Thank you. This is Alexander Sokol. I'll be presenting a 1-hour webinar. We'll try to finish in about 45 minutes so we have time for questions. And time permitting, depending on how many questions will be asked during the presentation, I will also show how to run the code, even though the body of the webinar is intended also for non-programmers. So I will start from slides, then I'll show how to download the code from GitHub, and then I'll show how to run it. All right. So just before I begin, very brief summary of what I will be presenting. There've been a lot of seminars already on adjoint algorithmic differentiation, which certainly is, at least in my view, is one of the most important, or if not the most important, innovation in quant finance in recent years. But usually you hear something like, you have to rebuild your entire library from scratch. And this is probably the case if traditional AAD tools are used, because if you're dealing with individual doubles, you need to write your code in a particular way to reduce the tape size, which is the biggest problem normally of AAD implementations in practice. Namely, not of two examples, but actually trying to get your production library to run on AAD. However, recently we've discovered a technique called tape compression. Tape compression conceptually is the idea of compressing the tape, namely reducing the tape size not through changing your code, but through changing the code of the AAD library, such that it just doesn't generate large tape. Sort of like, if you have an audio file, it can be 10 megabytes for a song, right? But if you compress it using MP3, it will be 1 megabyte or less. So the idea essentially is to use a similar type of compression, and there is a lossless and lossy tape compression. And so far we've been able to implement the simplest way of tape compression, which is simply dealing with arrays as a single number as far as the tape is concerned. So today I will present, first of all, a strategy of how to convert your quant library to AAD, or how to begin using AAD without any massive re-engineering. I will also present an open source Apache licensed class library that's a front end to CPP-AD called TapeScript, which we are maintaining on GitHub. And you're certainly welcome to use it for academic or commercial projects. It is free and can be used for commercial purposes with no license fees. In order to demonstrate that this can actually be done for a large-scale quant library, we implemented AAD in QuantLib. So, our contribution to QuantLib, we intentionally limited ourselves to just making it adjoint. In ours, we intentionally did not really change any code or adapt any code to work better with adjoint. The idea essentially is to simply take the existing library and try to change as little code as possible to implement AAD, because our objective is to develop a better tool, TapeScript, which permits you to do it with your library. All right, so let me with that get started. First of all, just a brief introduction to adjoint algorithmic differentiation. So algorithmic differentiation in general is a process of transforming software program which calculates a set of results from a set of inputs in a program that also computes its derivatives. And it uses symbolic differentiation. For example, if you have to deal with something like an exponent or any special function, you do need to use symbolic differentiation to implement AAD with it, but it's not the same as symbolic differentiation, because, or if you wish, you can think of it as symbolic differentiation of plus, minus, and divide the basic arithmetic operations in your program. And symbolic differentiation is sometimes possible and sometimes is not, but for most computer programs, as long as you can deal with all of your special functions, the program is differentiable. You can implement AAD in any program. However, depending on the program and depending on how you're doing it, it may actually reduce performance or improve performance, and that's the key in what I'll be presenting. Okay, so now the forward mode of AAD computes the derivatives of results with respect to inputs faster and more accurately than bump and reprise. However, forward mode really doesn't give you anything. In most cases, forward mode doesn't give you much more than just a better precision, where you're taking essentially a limit of delta x to 0 derivative as opposed to a finite difference. The real advantage, or the breakthrough in quant finance, is the reverse mode. In the reverse mode, what it does is it computes derivatives with respect to the of results with respect to the inputs. And the reason this is possible is because, as I'll show in a moment, the way AAD works, what is one of the flavors of AAD we'll be using works, is that you record a tape, record what your program is doing in a binary buffer, which is called a tape. And then you play it backwards. And even though the calculation itself, you have no better chance of getting your inputs from your outputs than putting, a broken plate together by throwing pieces in the air. However, if you're talking about derivatives, you can actually play tape forward or backwards. So because using a chain rule, from a point of view of the chain rule, it doesn't really matter what the direction is. So you can just as easily compute derivative of outputs with respect to the inputs. And in practice, what it means is that if you computed something which depends on a lot of market data, like, for example, XVA, right, the XVA measure, and then you're interested in calculating its sensitivities with respect to the inputs, in this case, at the amount of time, which is theoretically, even though in practice it's hard to attain, not more than 4 times slower than the original calculation, you can get any number of fixes you want. And it sounds certainly mind-boggling, but actually it does work. Of course, there's no free lunch, right? In the sense that if you have twice as many input variables, your original calculation, which has to process all of these variables, will have to run twice as long. However, if you have after that twice as many sensitivities to compute, it still would take exactly the same time to compute them. And that's the amazing thing about it, because in finance, quant finance rather, you normally have a lot more inputs to a single output number than the output numbers. So, for example, you're computing a price, and you need 100 sensitivities for it if you count all of the buckets and so forth. So this gives you the ability to calculate it only slightly slower, several times slower than the original value. And what it means is that, these days actually, in most cases, especially if you're dealing with XVA, a single calculation is fast enough. But if you're doing multiple Greeks, you have to, go and get coffee or lunch, right? So here the idea is that you can avoid it. All right. So now the how to implement AAD for sorry, I think I skipped a few slides. 1 second. Actually, no, I'm good. Right. Now, and next point is how to implement AAD for an existing quant library. Okay. First of all, hand coding it, in my view, even though there are heroic efforts to do it by some teams, I know. Hand coding, I believe, is impractical, simply because, well, maybe practical for specific bottlenecks, but certainly not for large-scale library. Because going through every line, it's hard enough to build a large library, as we all know. And going through every single line of code, trying to figure out what the derivative would be, I think it's just absolutely impossible. Even though, as I said, there are teams that are doing it. And in particular, I believe OpenGamma is in the process of taking this specific approach, and they're promising, to my knowledge, something something that would be using head coding in Java. However, if your library is in C++, C#, or even in Java, if you're willing to use GNI to have a joint tape on the C++ side, you can actually use a different way, which is operator overloading. Okay, and now one other method of implementing AAD, which I will not recommend, the source transformation. Okay, so source transformation, it does not have this problem of hand coding that it does not require you to go through every line of code of your program and modify it. And it's automated, just like operator overloading is automated. The problem with source transformation, first of all, is that the most popular tool, which is Tapenade, is actually not free for commercial use. It's done by INRIA in France. Also, you have to send them your source code, and they will send you back, or upload rather, and they will send you back your transformed source code. In general, it's mostly, if you're doing academic research, your code may be in a single function, even though depending on what you're doing, it may not be. But if you're doing production library, your code is not in a single function. It's a huge class library with interfaces and so forth. And I don't believe the source code transformation tools are really capable of converting a very large scale library because, simply there is too much there. You have to change signatures of functions and so forth. So I believe the source transformation is good as an academic research tool, but it's not good for production. So one remaining approach, which is what I believe most of the teams that implemented AAD are using, is the operator overloading approach. So that, by the way, is the team that, the method that was was used by the Danske Bank team who implemented AAD in the production XPE library and received a System of the Year award last year for that. So how does it work? Okay, so operator overloading approach works. First of all, you have to do, and I know it sounds crazy, but actually it's not that bad. You have to replace all occurrences of double in your entire code with a user-defined class. For example, T double or A double or whatever you call it. Okay, and that replacement is going to touch every single source file. So people who are taking version control system update after you do that, they will be slightly surprised because every single file will change. However, there are a lot of code formatting tools and general code refactoring tools that make it possible to perform it with precision, free of error, and generally in a reliable way. And of course, if you have a good test suite, all of the test results will remain unchanged. It's very easy to test. What you do is that you replace your double with another class. For example, T double, A double, it can be anything that's not used. And then type def it back to double. And you need to make sure then that the results of your library are not changed. It still compiles, runs, and gives the same answer. So normally, yes, I mean it's definitely a large undertaking. If you do global replacement, some of your comments may end up with a joint variable in them as well. But typically, this is still something that can be done in a week or two, and it's not a big deal, even though it causes a lot of changes, because every single change you make is mechanical, just a global replacement. Right. In some cases, some people are lucky that they decided to use a different variable for separate reasons. For example, in QuantLib, which we used as a test case, Luigi and Ferdinanda, who are the founders of QuantLib, they had the idea that they would use double or single precision arithmetics, for performance, and that actually never came to pass. However, for this reason, instead of double, QuantLib uses real, which is for the capital type def. So it was very easy for us to convert QuantLib because it already used something other than double. So it was the real was type def to double, and now we just made it type def to T double, and that was it. So we've been able to convert QuantLib by changing to implement AAD in QuantLib by changing less than 500 lines of code, simply because it already used real. So we only had to fix the places where real was mixed up with double or some other minor compilation problems. Okay, however, before we start celebrating, after having replaced double with T double, we need to remember that that's not all. It's just the work only begins here, but it is a prerequisite in order to do the rest. Okay, now let me just show quickly some of the code that's needed to make a drop-in double replacement work on a large-scale library. Okay, so normally one would think if you are programming in C++, you would know that operator overloading makes it possible to create a class that behaves like double. Well, unfortunately, not quite. Namely, C++ compiler, and this is wired into the standard and cannot be changed. It treats native types such as double in a slightly different way from user-defined types such as T double or A double, as far as implicit conversions. So if you have a class which returns, like in QuantLib, for example, something called array, which is a class, and then that class rate can be converted through implicit conversion to double, you will get compile time errors. So the difference between TypeScript, which is the library that we have developed, and CPPAD, which is the library it uses as a backend, is that if you drop CPPAD joint variable into QuantLib, you get 100,000 errors. But if you drop TypeScript variable, you get 800 errors, right? So there is about 120 times improvement in how many compilation errors it causes. And below is in the slide is some of the code that has to be written in order to make this happen. So this, for example, this piece of code here makes it possible for T double to work properly with Boost. Right, so unfortunately, C++ compiler does not make it easy, but fortunately, it's still possible to overcome. So if you're considering doing a joint in this way, namely essentially making a global replacement of double in your library, even if you don't need tape compression, I would recommend to consider using TypeScript, because TypeScript is specifically designed to cause less than compile time errors when you're just doing this type of a global replacement. And then you can easily prove it by calling your variable something, and then doing, for example, A double, and then you can do type def to T double, or type def to this double, or an C variable. So this is something you can see for yourself in your library. All right, and some of these errors, by the way, that arise if you try to do that are extremely obscure. Like, for example, here's the error was reported on QuantLib forum that actually has to do with the conflict between Boost and CPPAT, but it was resolved in TypeScript. Right, so this is a commit or pull request to QuantLib where these changes were accepted. So actually, this code is already in QuantLib, and it runs with or without a joint. And we're going to post the entire converted QuantLib with test, which I will show today. It's not on GitHub yet because it was pointed out that most of people are using Linux and it doesn't compile on Linux yet. So as soon as we make it compile on Linux, which will probably be in a week or two, we'll post it to GitHub. But in the meantime, I'm going to demonstrate it today. It compiles on Windows. All right. So now the next, before I go to the next set of slides, do you have any questions so far? Questions? Anyway, please feel free to ask. However, the best way to ask them, I'm not sure if people can unmute themselves or not, is to type them into the chat window. So I'm watching the chat window, so feel free to use it to ask a question. All right. Okay. So next phase in this slide presentation is how does overloading library then work, right? So in other words, after you replaced your double with T double or A double, a specialized variable, how do you actually get a joint calculation? Okay, well, the way it works, and this applies not only to TypeScript but to all of the, or most rather, of the operator overloading libraries, is that there is a value mode, and the value mode is simply it works the same as a regular double and does nothing else, right? So this is when you don't need the derivative, simply because sometimes you still want to run your library when you're not computing any derivatives. Okay, so there is a tape recording mode in which you write a sequence of all operations to a binary buffer called a tape. And each, I'm still switching between different names. Let's say A double, right, or a joint variable holds a pointer to its own slot on a tape. And the size of the tape may become quite large because for example, if you're running Monte Carlo with 5,000 paths, every time you do anything with the Monte Carlo array, namely, a slice of numbers where there's like one number for each Monte Carlo path, you increase the tape size by 5,000 positions. And that's, by the way, what we're trying to avoid with TypeScript. Okay, and now the second is a tape playback mode in which the library reads the tape forward or backward to calculate derivatives. So forward mode is when you compute derivative of outputs with respect to the inputs and you read the tape forward. And for performance, just pure performance reasons, there is normally not compelling reason to do that because it's just equally fast, as a base calculation with a bump and reprise, except it gives you the infinite limit of delta x to 0. However, there are some practical uses of it. Like, for example, you can send your tape and a tape player to the cluster, right, or run it on GPU and so forth. So there are actually some uses of a forward mode which have to do with engineering, right? So when you want your calculation to run without going to a database all the time. But from a pure performance perspective, it's the reverse mode that's helpful here. But the same tape player usually is able to read the tape forward or backward. Okay, so some adjoint library like AAD supports several other modes. For example, tapeless scalar and tapeless vector. So this is not covered in CPPAD, so I will not be discussing them in detail, but essentially they have to do with being able to compute the derivatives without the tape, and they only work in forward mode. And because we always want to support the reverse mode, CPPAD did not include them, and TypeScript, which is based on CPPAD, with a wrapper rather around CPPAD, also does not include them. All right, so and this is a list of libraries. Okay, so CPPAD is our backend, and it's very model design. So if you're not using TypeScript, you should be using CPPAD, I believe. AAD is extremely well established, one of the first library, a lot of citations, but it's really research code. Basically, there are files with 6,000 lines of code in them. So I would definitely not recommend using AAD in any production because you look at it and it's very hard to understand, the code because it has a lot of flags, and these flags have to do with testing different versions of AAD. So I think it's more of a research. If you're a researcher in academia, I think it's a good idea to use AAD. But if you're doing production library conversion, then it's probably better to use CPPAD. And there's also a tool called Adapt, which is GPL. And that's why we're not mentioning or using it, because it's GPL. So, but you can use it, but we cannot use it because we distribute our code. All right. So, and finally, TapeScript is our library, which is the front end to CPPAD and is capable of tape compression. All right. So now, what is the tape? Okay. So the tape is sort of like assembler. So now, both in assembler and tape, variables are held in registers. And the executing program, which is the tape layer, processes instructions one by one, working with register locations. So, for example, there is a number in the first slot of the tape, in the second slot of the tape, and then you multiply them and put it in the third slot of the tape. And the only difference here is that it's worse than assembler, because in assembler you can have a loop, but in a tape you cannot have a loop, right? Even though we're planning to as additional enhancements to tape compression, we're probably adding to planning to add support for loops in TapeScript, but not yet. So normally in assembler you can have loops, but not in a tape. So it's almost like if you have 10,000 repetitions of something, that you have to actually explicitly write all of the operations 10,000 times. So it's worse than the assembler, and this explains why the assembler programs are big, but tape is even bigger. And tape can really, if you're not careful, can reach terabytes and cause a lot of I/O problems and kill performance this way. Right now, what is tape compression? Okay, so tape compression is the way to make the tape size smaller. For example, if you have an array and you do the same operation on every element of the array, you should be able to simply record a single operation saying, I multiply this array by this other array, instead of repeating it 10,000 times for each element. Okay, and tape compression can be lossless, like FLAC audio codec, right? So that reduces audio size without changing any bits. Or lossy, like MP3. Better compression, but it's causing some quality loss. Okay, so just as an example of how this works for AD, lossless tape compression is, for example, when you have an array, you can record the whole array in a single tape slot. Lossy is when you have, let's say, a time slice which records some dependence, and you do American Monte Carlo, and then just record the coefficients of the regression. Right. So in this case, instead of 10,000 numbers, you just have several numbers which are coefficients of the regression. And then you do derivatives with respect to them. So in this case, the regression is not representing the values exactly. It's an approximation. But it's even a further reduction in the size of the data that you're dealing with. So that's kind of a difference, right? So far we implemented only lossless tape compression. We're working on lossy tape compression for the next release of TapeScript. Okay, and now the next slide, which is one of the final slides, before I go into how to run the code, is problems that we will encounter if you try to do brute force AD for lattice and Monte Carlo. Okay, so what happens is that if you simply convert your library with to use a joint variable, and then you try to run Monte Carlo with options or barriers, you'll probably not get the right answer, or rather, for the barrier for the first derivative, the answer will be wrong, and for the option for the second. And the reason is that imagine that there is a binary option which pays 0, 1 depending on whether the barrier was hit. Let's say binary option, or binary which pays 0, 1 depending on where whether you are above or below the strike at maturity. So what happens is that if you slightly change the market data such that the barrier position changes, or rather the forward changes relative to the barrier, rather. In this case, this infinitesimal path shift will not cause any path across the barrier, so it still will be 0 and 1. So you will be finding that the derivative is 0, right? Because you had some paths in which the value of the option was 0, and some paths in which the value of the options was 1. Then you infinitesimally shifted the barrier, but none of the discrete paths was very close to it, so because they're discrete, right? So it means that each path that has 0 still has 0. In each path that has 1 still has 1. And what this means is that you will get a derivative which is 0 or some very small derivative due to discounting, whereas the real derivative is coming because the barrier position is shifted. So this problem is normally solved by smoothing, right? And that requires some fine tuning, right? So smoothing essentially is not taking the sharp barrier, but making it slowly go from 0 to 1 over some period of time, such that enough paths fall in the middle. And this is one solution. Another one is to use pathwise payoff derivative, right, which requires to change in the code. One one way that we're planning to implement, again, but it's not in TypeScript yet, is to implement a specialized function that will be aware of the barrier and essentially will record the delta function that arises when you shift it, right? And then propagate it properly when you, for example, do American Monte Carlo or lattice backward induction. So this slide, again, is something that we're planning for TypeScript version 4, right? So when you simply will be able to say, I would like American Monte Carlo, after, for example, applying max barrier to the entire time slice, it will do the right thing inside without actually doing anything outside, right? So it will be a simple interface that you simply tell the library what you would like to do with the numbers, and it will do everything inside. But again, we're not there yet. So far, if you need to use lattice or Monte Carlo with barriers, you need to do smoothing directly. For now, the recommended solution is smoothing, right? So making barrier not completely sharp. Okay, so any questions so far? Please type them again. Please type them to the chat. So it's about so about 25 minutes. So let me move now to how to use TypeScript. Okay, first of all, by the way, I'm going to use slides, so I quickly go through the material, and then, time permitting, I'm going to actually show how to do it online. So first of all, you have to go to github.com/compatibl and download it from a TypeScript repository. So you can fork or you can download. Of course, if you're using Git, it's better to fork because then you can merge with our updates. Okay, so then you choose the name with your replacement for double, right? So you can use a double. In this case, you can link with LLC or adept directly. For Quant, it's already done. The type is called real, and default name in TypeScript is tdouble. Right? So if you're only planning to use TypeScript, then tdouble is fine. Normally, by the way, if this tdouble or adouble or whatever you choose is not a frequently encountered string in code, then you can do further global replacement pretty easily because just the word double is frequently encountered. But as long as tdouble or adouble is not, then you can replace it with anything else. And then you replace double with this type name, and then type the effort to tdouble, right? If it's not tdouble already, and compile. Okay, most likely your code will not immediately compile. Okay, so first of all, if you find that your code does not compile and you correct TypeScript such that it does compile, certainly please do send us a pull request or email to team@compatibl.com, which is our committer ID for GitHub. That you found a problem and here's the fix, or at least at these early stages where we're trying to improve the library, we're providing free support. If you tell us that here's a snippet of code that doesn't compile, we'll do our best to make sure that it does compile. So please let us know. Right, and then after that, like in Quant, basically the change involved about 500 lines of code, and in your library, depending on what it uses and what third-party software it uses, for example, which version of Boost, there are some other libraries that people use, so it may be less or more than that. Okay, so then the next step is to do tape recording. Okay, so here's this this is kind of an API that more or less mirrors CPPAT. We're also working on a more advanced API, which we'll publish in one of the updates, probably in version 2.2. Which makes it easier to use a TypeScript when not all of the variables are in one place. I'll explain it in a moment, but let me first go through this one. So suppose that we would like to compute y equal to 2x0 plus x1, and we would like to find derivatives at x0 equal 2 and x1 equal 3. Okay, so first of all, we create a vector of tdouble, size 2, and then we initialize it with these two variables, values 2 and 3. Then we declare the vector as independent and start recording. And this is done by tape start of x, right? So essentially, we're saying that these variables, independent variables, so independent in AAD parlance, independent variables are the variables with respect to which you are taking the derivative. And dependent variables are those that you're taking derivative of. So you declare that you would like to differentiate with respect to x, and this is an array, so there are two of them. And tape start begins the tape. Okay, the output, you can then compute the output, and then, which is in this line, right? And then you create tfunc, right, which is an object holding a function from x and y, right? So why is x passed here? Well, because you may create a function in which not all of the input variables are engaged, and then another function in which additional input variables are engaged. So this makes it possible to have more targeted set of functions if you're having a single calculation that computes many outputs and uses many inputs. Okay, so what is the disadvantage of this interface if you're not doing research? Well, what happens in a production software program is that you normally get some market data from the database and then you use it somewhere, right? And you start calculating, for example, you build a yield curve. And then you get some other market data in the database, like, for example, volatility, and then you calibrate your model. So these two places are not in the same location. So it's kind of difficult from an engineering perspective to actually formulate your, or wrap your entire software program into this single neat function that takes inputs and outputs. More likely, you are reading some stuff from the database in various places in your program, and then eventually you're producing some numbers, and you're then saving them again to your database or whatever is your permanent storage, or displaying them in various places in your program. So we've developed a new API, which is not yet in this presentation, it's not yet on GitHub, but it will be there probably within a few weeks for version 2.2, in which you'll be able to simply say, here's the new independent variable with this string tag, and later here's another one, and then here's another output with the string tag, and so forth. So essentially, you will be able to call, to declare something as independent variable, namely an input, or dependent variable, or namely the result, in any place in your program. And then still in the end, you create this tfunc, but you will be creating it in this case from the string labels, right? So you give it a unique string ID. For example, market data dot, let's say USD dot, swap rate dot to Y, right? So you can create any type of a numerology for the market data. And that, we believe, will be, even though it seems trivial, if you're dealing with research code that's anyway in a single function, but actually I believe this will be extremely convenient, to use as opposed to the standard API. But so, if you believe that this will make a difference, please watch us on GitHub, and soon you'll see that update. All right, so now the next step is playing the tape, right? So in order to play the tape, you simply create the vector of inputs for which you would like to calculate the result, and then you specify which derivative you would like to calculate, for example, first derivative, and then you just get output as a function of the input using function f, which is invoked on this object. So f is our functor, or object holding the function or tape. And you say f dot forward, right? And this is what the tape contains, right? So the tape, of course, is binary. And for the moment, we're using CPPAD tape, even though, we made some modifications for the tape to hold arrays as well. But for now, we're using the rest of the infrastructure from CPPAD. And this is how it looks. So the tape itself is first record in the tape is init, right? So we're initializing the first variable, right, which was which is the first line of the code in the previous slide. Then we're initializing the second variable. Okay, then we're multiplying, and then we're adding, right? So if we go back, right, so we initialize this variable, then this variable, then we are multiplying this variable by number 2. I'm not sure actually if you can say, I just realized you probably cannot see my pointer, so I wonder if I can. Let's see. I think I can use this to annotate, right? Yeah. My apologies. I was pointing with a pointer, but I just realized that you probably cannot see it, right? So initializing this first, and then the second, and then you're multiplying these two things, and then you're adding everything together. So this is the sequence of operations that you have on this slide, right? And as a result of that, you're getting the derivative, right? So you're getting the value here, right? Because you're getting 1 and 0. So you get 3, then you multiply by 2, you get 6. And then you add 3, you get 9, right? So if you look at the formula, right, you have 3 times 2 is 6 and 9, right? Okay, and here you're getting the derivative, right? So you're getting derivative is equal to 2. Okay, and again, this is very simple. It's just a chain rule. Okay, well, the magic happens in reverse mode, right? So in reverse mode, you're doing the same thing reverse. You have you're initializing the vector of results, and then you're calling the function of reverse to get the vector of inputs. And what happens here is that the same tape is played backwards, right? So you start from the end, from plus, then multiply, then init, which is where you get your outputs. And the reason this works is because if you have any type of arithmetic expression, and all of the software programs eventually boil down to arithmetic expressions, you can just as easily ask how much do you need to change this input such that the output changed by a certain number, as well as, well, if I change this output without changing any of the other outputs, how much will the inputs change such that the result is correct. And that, in other words, you cannot obtain input from the output, the number itself, but you can compute the derivative in both directions because it's the derivative, and that's how it works. So I think I don't want to stop and go line by line because of the limited format of this webinar. But I'm also doing some workshops with WBS for this at various with WBS conferences. So in a workshop, that we actually go and go line by line and try to understand exactly how it works, because it's really, certainly I would encourage doing it using our example, because it's very helpful to actually understand exactly how it works, because then it's easier to understand what performance limitations are there and so forth. All right, so now next slide is power, right? So, well, in this case, power is, as you can see here, there are two multiplications. So the compiler knows that to take power 4 is x times x, and then the result times the result, right? So it's takes squared 2 times, which as you can see here, right? And then, however, when the exponent happens, we don't actually go and record and untape every arithmetic operation that's inside the exponent, especially because it's coded normally in assembler. What happens here is that your adjoint library, such as CPPAD, for example, would have to know about the exponent and know how to compute its derivative. So the quality of that joint library is not only in the quality of performance of how it records the tape, but also it has it has a lot to do with its ability to support special functions as well that you need. And one of the complex things here is also the complex numbers, to which I will get in a moment. By the way, we're running a bit behind, so let me just accelerate slightly. Okay, you can get trigonometric functions, right? So this is how the tape is recording for trigonometric functions. Also, you can see that sine and cosine here explicitly in the tape slot. And this is a kind of very short guide to our variables, right? So there's t double, which is a tape double variable. There's a tape function. And now, if you need to use complex numbers, and there are a lot of calculations we should do. Like, for example, Hessian model calibration uses complex numbers. And generally, if you look at Quant, there is a lot of stuff that uses complex numbers. And another one, of course, is FFT, right? Fast Fourier transform. It actually turns out that it's not that easy to put T double into complex, because complex, to be properly vectorized and so forth, assumes a lot or has to know a lot about the properties of the underlying variable. So if you put, for example, CPPAD double into complex, it will not work. But with TapeScript, it actually does work, and that required a lot of code. You can actually examine the header to see what I mean. So it works with complex. And TapeScript also provides tape serializer, where you can actually output this tape log, to see what's happening. And also it provides binary serializer in case you would like to serialize a tape and then save it somewhere. And the performance is, for example, that if you do dot product of two vectors of size of I guess 100 million, well, that's how many ticks it takes, and really that's not a lot. What we're calculating here is how much slower would it be with T double than with regular double, and essentially the overhead is absolutely minimal. Okay, now special functions, as I mentioned, you need to do analytical differentiation, and then the TapeScript or CPPAD has to support them. And this is already done, but you may need to extend it if you're using any type of a special function we don't support. But again, please feel free to call or email or submit a request on or ticket on GitHub to requesting us to do it. And there are a few slides here on how it works with complex numbers for FFT, which I will skip. Okay, and now finally, before I go to the actual code, here's a tape compression. Okay, so how does it work? Okay, so we implement the tape compression in version 2 of TapeScript by simply making it possible to record in a single tape slot either a double or an array of doubles. So double or array of doubles. And this is done currently using something called T-object. So T-object can convert to T-array or T-double. And we were planning to slightly improve the syntax such that it's easier to get compile time error if you're not combining them in the right way. But it already works, and it's just simply going to become a little bit safer. So for now, there are more conversions. There will be less conversions in the future. And then everything that here's the recorded tape, right? So for the array of size 2. So you can see that here is the tape looks exactly the same as it did before when these were scalars, except that in each slot there's a array of size 2. Right, so it's exactly the same thing. However, imagine that if you're doing Monte Carlo, and this is an array of size 5,000 because you have 5,000 paths. So with that, you still have a single tape record saying you multiplied a number in slot 1 in slot 2 and obtained something in slot 3. And she said, like it says, for example, this slot 3 is multiply. First operand is in slot 2. Second operand is in slot 1. So there will be 5,000 of these records if you're doing single double, but there's only one of them if you're doing it using tape script with tape compression using array. So that's essentially is the key performance optimization here. In TRA, it's most effective if you just do arithmetics on the entire array. However, you can actually get element by element access to it if you have to, but that's less efficient. Okay, and there are a few examples we implemented, which can be used to demonstrate performance. There is linear regression, there is quadratic regression. Generally, we implemented arbitrary power of regression, such that we can use it for American Monte Carlo. And these are various tapes for that. Here's of course the tape size depending on how many variables, and of course it's flat and constant if you're just packing them into an array. And this is a typical performance calculations, for doing calculations, which you have to do in because of the way that we're testing with Quant. So far, we're mostly doing things like, let's price, let's say 100 forwards and compute bucket sensitivity. So let's price 100 options and compute all the delta for all of them. So any of these curves that are linear, it means that the number of sensitivities is the same. It's just we're growing the size of the portfolio because we're dealing with vector essentially. In which, if you have a portfolio of options, then each slot of the vector is dealing with one option. So this is without adjoint, with by finding bump and reprise, without compression and with compression. So this first, second, and third, right? So with compression is the best. This is just compressed without. So this is a finite difference. This is compressed to get faster. This is for FRAs, so it's quadratic because this time we're increasing the number of forward rate agreements and also increasing the number of sensitivities. So assume that, for example, you are doing, let's say, XV on the portfolio, and then the more instruments you have, the more sensitivities you also have. So again, here, this is brute force, and this is compressed tape. So you're definitely getting performance, which, depending on the example, it can be from a factor of 2 to a factor of about 20 or so. So normally I would say something like 5 or 10 is typical, and what it means is that something that used to compute a minute, it will compute in 10 seconds, which certainly is a lot of difference. All right, so now finally, last slide before I go and show some of the code is TapeScript release schedule. So phase 1.6 was released in May 2015. And it was simply a drop-in replacement of double with CPP AT backend that made it possible to compile and run Quantlib as a case study, right? So that did not have any compression, but it made it possible to replace double with T-double more easily. Okay, so phase 2.1, which is released 2 days ago, is a lossless tape compression for arrays, validated performance gain for typical finance examples, and it's now completed. This replaced phase 2.0, which was released about a month ago. Okay, phase 3, planned for the first 2 quarters of the, probably more realistically second quarter of next year, is lossy tape compression and specialized techniques for lattices, Monte Carlo, and MC. And finally, phase 4 is loops and high-level expression on tape with custom containers and embedded code. So, so the first 2 releases are completed, and the next ones we're announcing. And finally, before I go to code, TapeScript, including all performance optimizations, is Apache license open source and will always remain free for commercial use. So we certainly welcome everybody to use it for research or for production libraries and banks. and of course our competitors or partners, and anybody in the industry, even if you're a software vendor, please feel free to use it, because that's what open source is about. But if you do use it, we certainly hope that you will consider also contributing your changes or improvements to GitHub, even though you don't have to do it. All right. Any questions so far? It will be a good time to type them because I'll still be watching the chat, but I'm going to share the screen and show how to run init code, and hopefully we'll have a little bit of time left. All right. So with that, let me go and share the screen. Okay. So first of all, where's the code? Okay. So there's a github.com. And then this CompatibL. And if you go to CompatibL, you'll see Quant lib. It's our fork and the TypeScript, right? So the Quant lib, we did do a fork which prevented problems with compilation. However, we still haven't pushed all of our tests, which I'll show now, to GitHub because we're fixing Linux compilation, or GC rather. So TypeScript is already compiling on Windows Visual Studio and GCC, so we already pushed the update. And the TypeScript repository here, so this is the source code. It's about 300 commits at this point. Two contributors, because Peter Kaspers kindly contributed, the fix. And there are three branches, right? So there are release 2.0, which is soon to become obsolete, release 2.1, and master, which is for now the same as release 2.1. Okay, so by the way, if you are not new to GitHub, this is a premier collaboration site for open source. And if you would like to communicate with us, you can post an issue using this link on the right. Or you can post a pull request. A pull request is something you do when you fork using this button. So it creates your own copy of the repository. You make some changes to it, and then you can package them in a pull request, which means that you're asking us to pull or import your changes. And in this case, it's open source, right? So you don't get compensated, but you get fame, and recognition. And certainly, for example, if you're a vendor or consultant, you see that here's CompatibL, and here's Peter Kaspers. Well, we would like this to become a community, so there will be more people there. And of course, the more you contribute, the more you can use it, I guess, to claim, claim, your pieces, being the piece that you had written, right? Because this is open source Apache license, but everybody retains their own copyright. Okay, in order to download this thing, you need to clone it, right? So there's a clone button here, so you copy to clipboard this URL. And you can use various tools for that. If you're working with open source, you can use SmartGit, which is paid for commercial use and free for open source. But there is any number of other tools, and this gives you the log or revision history, right? So this is the Git revision history, and I can also open the folder and actually run the example. So, for example, you see what here, this output files, right? So I'm going to delete the output files. I can look on Git and make sure that the output file is really deleted, right? So this shows that the file is missing. And then I'm going back to, let's see, this is what TypeScript, okay. So I'm going to run the code which I previously compiled. And this will, I didn't compile it, okay, that's fine. Right, so this is all of the examples, right? And now we get again this files that I just deleted, and Git doesn't show them as deleted anymore. And here in these files, if you look at what the files are, you can see that, for example, there are performance tests here, right? So there are results for performance tests. By the way, these are not recorded on Git because otherwise they will change every time you run on a new machine or slightly different temperature. But everything that's not involving performance numbers is recorded on Git. And here the tape is, there are some tape outputs here, right? So you can actually look into this result and see exactly what the tape is doing and so forth. So this is a log file written by executing code. And the library consists of boost, which we put in the dependencies folder right here. So, so if you look at the TypeScript repository, it has dependencies folder. In the dependencies folder, we have CPPAD and boost. right? So we included our own version, but if you don't like that, if you have your own version of CPP AD and Boost, you can simply change the path. And then our code is in tape script, so this is the C++ code. And the only header you need to include is this header tape.hvp. The rest is linked from there. And then the examples are in examples and impl, right? So you can go, for example, here. And this is the code for testing adjoint differentiation for linear regression. Okay, so now next thing I wanted to show is and by the way, you can very easily step through examples with the debugger. So what it means is that you can see exactly what's going on, and you can see the. Okay, so for example, you can set a debugger breakpoint somewhere here. I don't know, I'm not sure I hope I'm saying it in the right place, but okay, so it ended up. So basically, you can now look and see that this X, right, and it has pointed to the tape, right? So so you can see that there's a value 3, tape ID is 4, which means that that this is the tape number 4, which is CPP has 1 tape per thread, and it's stored as slot 2, and it has a value of 3. So what I have on the screen right now is exactly the same example that was on the slide, right? So you can see here y is equal to 2x plus x1. So this is the same thing as on the slide. And you can see exactly which slots are taken by each variable. So you can see what it's doing and follow through code. So this is the add example. So this is the example that was used for the slides. Okay, and finally for QuantLib, this is the QuantLib download. Again, you can basically if you're interested in the QuantLib, if you want to try your own examples, you can already take this code. And there's a branch here called master adjoint, which has adjoint on, and master adjoint ready, which just does the changes which prevent adjoint code from compiling, but does not actually replace the real with the adjoint variable. So that is something that Luigi is not periodically pulling into the QuantLib master. And this is where you actually replace double in QuantLib with adjoint variable. However, there are no examples here yet, right? So in order to get examples, you can fork that, and then a couple of weeks later you can see the update, and the new code will be downloaded when you click refresh. And the way this works is that if you open, if you open the QuantLib repository and let's say Reveal and Explorer, right, which will open. So here there is a QuantLib. So all of these folders, for those of you who are familiar with QuantLib, all of these folders are pretty standard. However, we added dependencies where Boost is located. We added tape script, which is the tape script is located, and we added something called QuantLib adjoint. So QuantLib adjoint shares the source code with the rest, but has its own solution with different compile time settings. And also it has its own examples, right? So there's this test suite, and all of the examples in the test suite which start from adjoint. These are the examples, so there are about 130 examples. So these are the examples that are using in some way algorithmic differentiation, even though some of them perhaps is more for testing tape script as opposed to something you would do in practice. So one thing, again, I want to emphasize that just to preempt any comments on that, the way that we implemented adjoint in QuantLib was to prove that we can do it in a large-scale library and to stress test the tape script, right? So in other words, we're not, this is our primary objective as opposed to making anything, production-like out of QuantLib, even though, companies or banks who are using QuantLib for production would probably have a slightly different objective, but we don't use QuantLib for production. We're using it essentially as an excellent, with actually one and only, I guess, well-established open source library for quant finance that we're able to demonstrate how TapeScript works in a large-scale quant library. So some of these examples that we have are examples more demonstrating what TapeScript can do as opposed to anything you would do in practice, like, for example, doing a portfolio of 100 FRAs. Please keep this in mind when you're looking at this. Okay, so well, with that, I'll probably should stop and ask for questions because this examples run a few minutes, but you can see they started running, right? So there are 136 test cases, and they have similar idea that they write output to TXT files. All right, so with that, let me go to chat and see if there are any questions. One moment. Okay, Bobby. So I think that this is the point at which we should ask for questions and wrap up. So I'm not sure if you have any rescans or if people would be typing questions into the chat. Okay, so I got one question offline, not through WebEx, so let me answer that one. Okay, so right, so it was a clarification about this new interface that I was talking about. So so the existing interface of how to create independent variable and then create a function tfunc and then do forward and reverse will remain. Right, so this interface is parallel to CPPAD, and it's probably anyway the easiest interface if you're doing something research oriented, in which your function that you're differentiating is a single function. However, the other interface, which will be in release 2.2, and that will be released, well, let me make a commitment, will be released by November 30th, right? Even though most likely it will be earlier, right? So within 1 month. Okay, so that interface is the only interface that you should consider using in a large-scale library because, as I mentioned, half an hour ago, the main problem with traditional interfaces to adjoint libraries, such as CPPAD, AAD or any other, is that it requires you to formulate or encapsulate your entire calculation as a function. And it's very difficult to do it. So you have to specify all of the independent variables at the time that you start recording the tape, and then you have to gather all of the outputs at the time that you stop recording the tape. And in production libraries, that's not specifically designed for AD especially, is never in one place. So this interface essentially makes it possible for you to create a numerology, which you may already have for your own purposes, of various types of market data. Like, for example, Bloomberg has its own mnemonics, Reuters has their own mnemonics, and every normal quant library would have some sort of mnemonic for market data, as well as you need mnemonics for the output as well. And then you're simply providing string IDs. So you're saying first independent variable, let's say, is the let's say Euro USD FX rate. And a second independent variable is the first bucket of the swap rate, with 1 year swap, second bucket is 2 year swap, and so forth. So in other words, you can assign, you can declare independent variables step by step as you're already doing the calculation. And this makes it possible to, for example, load the yield curve, do some calculations with the yield curve, then later load the volatility and declare volatility as another set of independent variables. And then you produce, let's say, prices and declare them as dependent variables. And then you produce XVA and declare it as a final dependent variable. And then you create a functor, which you can, for example, say, I want just XVA with respect to all of the initial market inputs. Great, okay. Or you want XVA with respect to the prices, right? So you can only do more sophisticated things in which you take two intermediate results and compute, basically take the segment of the tape between them. Like, for example, if you're trying to do Euler allocation of Euler-based allocation of marginal allocation of let's say XVA, you will be able to actually use prices as dependent variables, is independent variables, and XVA is dependent variable. So so this, I think, is the only interface that you should consider using in production environment, and this will be released in TypeScript version 2.2. How to get 2.2? Again, visit us, follow us on GitHub. So you can. You can follow, actually, where is it? You can follow, there's somewhere a follow button here. I guess I don't see it because it's my own repository. And you can fork, right? So several people already forked the repository. And this way, when the release appears, you simply get every time you refresh. And if you follow, you get a message. Or if you get a refresh, the new version will come to your computer via Git. But of course, if you're not using Git, you can always, get either regular download or, please write to us at team@compatibl.com and we'll be happy to send you a package. Currently, TypeScript is supporting GCC and it's supporting Visual Studio 13 and 15. By the way, one thing I should have mentioned is TypeScript is C++ 11 because some of the optimizations or techniques that we're using are not available on C++ 19. So this requires C++ 11. But, it's pretty standard these days. All right, so with that, it's exactly 1 hour. So unless there are any more questions, we're probably ready to wrap up. Thank you.